All right, so now we're going to talk about section 5.4, the inverses of exponential functions. All right, so here's your notes. You can pause the video and copy them down, and then I'll kind of talk about them as I walk through them. So the output of a logarithmic function tells you what exponent you must raise the base to arrive at the input. So we've actually talked a little bit about this. Remember, we talked about log base 2 of 8, and we ask ourselves 2 raised to what power would give us 8? And the answer is 3. And that's what it's saying right here. The output of the logarithmic function, boom, there's the output, tells you what exponent you must raise the base, boom, there's the base, to arrive at the input. And this is your input. So when you have log base b of x, if that's equaling your answer y, what that means when you write it in you can rewrite this thing in exponential form because they're inverses, and you're saying b to the y power equals x. So you can say b to the y power equals x. 2 power y equals, can't spell, x. So right there are two very effective and useful ways for us to write the exact same expression. Now, if there is no subscript, and by subscript we're talking about the base down here, if no subscript is given, you are to assume that b, the base, is 10. This is called a common log. And you would read that the common log of x, or the log base 10 of x. If the base is e, we use the natural log. In other words, the log base e of x is the same thing as ln of x. And you'll see that button ln on your calculator. That is the log base e. Now, one of the reasons why we have a log base e is because, as we've talked about, the value of e pops up continuously all over the place in calculations of natural effects. Physics, biology, all kinds all over the place. Now, when we talk about log functions, we're talking about, when we talk about the properties of log functions, we're talking about all base logs, like this one, and the natural log, and the common log, and all those log base whatever, as long as b is a positive number that's not equal to 0, that's not equal to 1, and if you remember, that is the exact same rule we had for the exponential base b. The log base b and the exponential base b are the same number. Remember, that base b has to be positive, and it cannot equal 1, because if we have 1 to the 10 millionth power, it's still just 1. It's not going to behave like an exponential. And the rules are there so that everything that we call an exponential is going to behave in a similar way. So when we look at the log, same thing holds true for the b, and what we're going to end up with is we cannot have a negative number here. Because if our b is negative, is always positive, there's no way we can raise a positive number to any power and get a negative number output. So that's why that's always going to be positive. So the domain for the log functions, all of them, are x is greater than 0, and the range is all real numbers. Now, the domain is x is greater than 0 since powers of b being positive number that's not equal to 1, if we raise that number to a power, they're always going to be positive. There's never going to be a negative 1 like we were talking about just a second ago, and it's never going to be 0. You're never going to take 3 and raise it to any power where it's going to be equal to 0. You're also never going to raise 3 to any power and get a negative 3. It just doesn't happen. That's mathematically impossible. So that's what we're talking about when we're talking about the domain. Because remember, the domain here are what b is raised to some power to get. Now the range r, remember that's the output. That's going to be your y value over here, and those are the exponents, and the exponents can be any real number. Remember, if we have 2 to the x, we can plug any value in there we want to. We can plug a negative in, it's going to make it into a fraction. We can plug in 0, it's going to make it 1. We can plug in 1 and our positive number, and it's just going to get bigger and bigger and bigger. So exponents can be negative or positive. So remember, this is the exponent. It's just in log form. It's the actual output value. All right, so let's evaluate each log, and then we're going to rewrite the thing in exponential form. So first thing I'm going to do is I'm going to go through and I'm going to evaluate all these, and then we'll come back and write them in the exponential form. So literally the question we're asked, what power do I raise 2 up to get 32? And the answer is going to be 5. Part B, what answer would I raise 5 to get 5? Well, that would be a power of 1. 5 to the power of 1 gives me 5. 36 raised to what power gives me 6? This one's kind of tricky. You've got to think and remember about the fractional exponents. Remember, if I have 4 and I have a fractional exponent or even a decimal exponent, remember what you're actually doing there is you're raising it to this power and you're taking that root. So 4 to the 1/2 power is actually equal to the square root of 4, which is 2. So if we take 36, we're going to have to take the square root of it to get 6. So that's going to be 1/2. Now, when we get into the negatives, remember that's what's going to flip things to the bottom. If we took 4 and raise it to the -1 power, remember that is not the inverse. That is an actual power of -1. If it's f to the -1 of x, that's the inverse. Here, that's signifying the reciprocal, 1/4. So you're going to flip it to the bottom and make it a positive exponent. So if this had been -2, you're going to flip it to the bottom. That's going to change the exponent sign from positive to negative, or sorry, negative to positive, and then you can simplify that, and that's going to be 1/16. And that's what you're dealing with here. And remember, there is no subscript here, so this is understood to be a log base 10. So 10 to what power is going to give you 1/100? Well, the over means we're going to have a negative. And then what power would we raise 10 to get 100? Well, that would be 2. So -2. Negative flips it to the bottom, makes the fraction, and the 2 makes the 10 into 100 when you raise it to that power. All right, and e, natural log of e to the third. Well, here's the thing. Until you get really comfortable with this, rewrite it. Log base e of e to the third. Now, all you're doing is you're saying e raised to what power equals e to the third power? Well, that would be 3. You would have to raise e to the third power to equal the value of that thing right there. All right, tables are shown for two functions, f and g. Complete the tables. So we've got an exponential here with base of 3. So we're going to do 3 to the negative 1 power. That's going to be 1/3, because remember the negative drops it to the bottom. 3 to the 0 power is going to give you 1. 3 to the first power is going to give you 3. 3 to the second power is going to give you 9. And 3 to the third power is going to give you 27. All right, here we're doing the log base 3, so we're asking what power we've got to raise 3 to get that. So we know that's going to be negative 1. What power will we raise 3 to get 1? It would be 0. What power do we raise 3 to get 3? That would be 1. What power? 3 to what power gives me 9? 2. 3 to what power gives me 81? That's going to be 4. And if we had a 27 in here, that would be 3. So what's the relationship between f and g? How could someone tell just by looking at the entries in the table? Well, f and g are inverses. And they're inverses because one function undoes what the previous function, what the other function did. And how do we know that? How can we look at this and tell? Well, if we plug in 1, we get 1/3 in this one. And if we plug in 1/3, we get negative 1. We get the same, we plug in and it gets this, and then we take that and we plug it into the other one, and it gets us the thing we started off with. And that's true all the way down through here. Now, they threw you a little curveball here with the 81 and got it out of order, but it's still going to happen. You plug in 3, you get 27. You take the log base 3 of 27, you're going to get 3. It's going to give you the exact same number you started off with. All right, so find g of f of x and f of g of x. What does the result tell you? So first, let's find g of f of x. So that's going to be the log base 3 of x. But then I'm going to put the f of x in place of the x in the original function, 3 to the x power. So now, what do we know and what do we find? Well, we're saying 3 to what power is going to give us the value of 3 to the x. So that's going to be x. All right, and in the same way, if we do it the other way, we've got 3 to the x power, but we're going to write in g of x in place of that x. So log base 3 of x. Now, we're going to learn this later, but this is a special rule here, and we actually can use this, but just trust me for now, it's equal to x. So, if we do the composites and they both equal x, since the composites equal x, this means they are inverses. Let's scroll down. Now, complete the following sentence with the words additively or multiplicatively. So that's what's going to go here. So what we're looking for is as the inputs of f grow. Inputs are x. So as this grows, and how is it growing? Well, we're adding 1, we're adding 1, we're adding 1, we're adding 1. So the inputs of f are going to grow additively. The outputs of f grow what? Well, 1/3 to 1, 1 to 3, 3 to 9, 9 to 27. Hopefully you can see that that's multiplying by 3 each time. Times 3, times 3, times 3, times 3. So it's going to grow multiplicatively. And when we're looking at the g of x, what do we know? As the inputs of g grow, 1/3, 1, 3, 9, and then of course we would have the 27 in here, and then the 81. It's going to be multiplied by 3 each time, so multiplicatively. The outputs of g, -1, 0, 1, 2, 3, 4, additively. Now, that makes sense because what do we know? With the log, the outputs are growing additively because we're adding one more time that we're multiplying 3. We're multiplying times 3, we're multiplying times 3, we're multiplying times 3. So every time you multiply by 3, the exponent that you're expecting here, this to equal, is going to be increasing by 1 each time you multiply by 3. So since this is multiplying by 3 each time, then your outputs are going to go up by 1 because you're adding one more time that you're multiplying by 3. Because remember, the answer to a log problem is your exponent that you're looking for. It's the exponent that the base was raised to get what you're evaluating. All right, hope that helped.